And the first talk, as you heard, is by the Revd Dr John Polkinghorne. And actually that title, Revd Doctor, tells you quite a lot about his career. For 25 years he was a theoretical elementary physicist, ending up as professor of particle physics. Yeah, sorry about that, elementary particle physics. It was a compliment actually, because if you're very clever and you can explain things in elementary ways, I think that's a great virtue. And in fact, a lot of the fellowship applications for Cambridge colleges say you have to explain what you're doing in 5 lines to the intelligent layman. And actually John is exceedingly good at explaining incredibly complicated things in a very accessible way, and that's one of the reasons we're very pleased he's here today. The other anecdote I can tell you, and I suspect it will be the same today, is that he will talk for an hour very eruditely, and he'll just have a back of an envelope with 6 keywords on it. I don't know if that's true today. Maybe you've got a fresh sheet of paper with 6 keywords on it, and I'm always incredibly impressed by that. Well, let me finish telling you, after he did elementary physics, elementary particle physics in Cambridge, he was then ordained to the Anglican priesthood and has spent the second half of his career marrying science and religion, to the great benefit of many people. Of course, he's done many other things. He was president of Queen's College here in Cambridge, and he's been knighted, and in 2002 he won the Templeton Prize for Science and Religion. So it's particularly apposite that this course is underwritten by the Templeton Foundation, so we're particularly glad to have him. He's written many books, of course, and some of them are on sale out there, so do take advantage of that, because they're cheaper from us than they will be in the shop. So without further ado, let me hand over to John. He's going to explain to us why is physics possible. Thank you, John.
Thank you, Paul. Well, let me start off by asking the question, why do we do research in physics? Like any other worthwhile activity, it has its fair share of rather wearisome routine. It also has its fair share of frustrations. I was a theoretical physicist, as you just heard, and at the end of a working day, my waste paper basket might very well contain a number of pieces of crumpled paper as the good ideas of the morning proved less persuasive in the cold light of the afternoon. It's hard work, but why do we do it? Well, we do it, basically, I think, because we want to understand the world. That's the thing, I think, the motivation that drives physicists. And physics has been astonishingly successful in its quest for understanding. Of course, that's partly because physics has had a limited ambition. It doesn't seek to ask every question about what's going on in the world. Essentially, it asks the question of how things happen, the questions of process, if you like. And it limits itself to considering a certain kind of impersonal encounter with reality, situations where you can repeat what's going on as often as you like, not unique in the way that all personal encounters are. And that gives, of course, physics its secret weapon, which is experiment, the possibility of repeated testing and verification of what is claimed to be happening. I mean, I was, as you heard, a theoretical physicist, but I would gladly acknowledge that my subject during the 25 years I worked in it was very largely experimentally driven. And the theorists were limping along behind the experimentalists, seeking to make sense of the new patterns of the subatomic world that were being disclosed to their investigations. So we do physics to understand the world, and we're very successful at doing it. And it's quite a popular strategy these days to try and explain human capabilities in terms of an evolutionary origin. Say that evolutionary necessity has shaped our brains in such a way that our minds are able to grasp what's going on in the world. And of course, there's a certain amount of truth in there. It's clear, for example, if we couldn't figure out that it's a bad idea to step off the top of a high cliff, we wouldn't stay around for very long. We'd stay around rather longer in East Anglia than we would in many parts of the country, but you know, you have to be able to cope with everyday experience. But our ability to understand the world, of course, vastly exceeds anything that is, in my view, explicable in those terms, or indeed could be considered to be a happy accidental spin-off from abilities developed in that area. We are able to understand regimes that are totally different in their character from the world of every day. I'm going to talk a bit about quantum theory tomorrow, as Chris Isham is also going to do. And we all know, of course, that the quantum world is totally different in its character from the everyday world. It is cloudy and fitful, and we need for it counterintuitive modes of thinking. We need to be able to think in terms of superposition. We need to consider the existence of states which are mixtures of being here and being there, which is not exactly an everyday concept to deal with. So it's one thing to say that the high cliff is dangerous, but it's a different thing to realize when someone like Isaac Newton comes along and in the astonishing creative leap of the human imagination sees that the force that makes the higher cliff dangerous is the same force that holds the moon in its orbit around the Earth and the Earth in its orbit around the Sun, discover the mathematically beautiful universal law of inverse square law of gravity, and in terms of that explain the behavior of the whole solar system. You may remember, if you're a Sherlock Holmes fan, that when Holmes and Watson first meet, it's in The Study in Scarlet, they're having a conversation, I think it's over breakfast in a London hotel, and right from the start Holmes is pulling Watson's leg, and Holmes says to him in the course of the conversation, "I don't know," he says, "I don't know, does the Earth go around the Sun, or does the Sun go around the Earth?" And of course the good doctor is horrified. There's apparent ignorance on the part of the great detective, and Holmes simply says to him, "What does it matter? For my daily work as a detective, in other words, it doesn't matter at all. We know many things that we don't need for everyday survival, everyday coping, but which we are able to acquire, and we are able to discover and formulate the counterintuitive modes of thinking that fit the behavior of that aspect of reality." And of course, as we all know, that in some sense the mystery of our scientific ability to understand the world in a deep and profound way is yet more deep and profound than that, because it turns out that it is mathematics which is the key to unlock the secrets of the universe. It's an actual technique in fundamental physics to seek theories which in their mathematical expression are characterized by equations that are beautiful equations. Usually when I give this sort of talk, I have to then spend a little passage explaining to people in the audience what mathematical beauty is. Of course, you can't actually succeed in doing that. All forms of beauty are easier to experience than to describe, but I'm sure I don't need to do that with this particular audience. As we all know, that mathematical beauty is concerned with qualities like elegance and economy and that peculiar property the mathematicians call being deep, by which a very simple sort of description turns out to have immensely complex and fascinating consequences. Mathematical beauty is certainly something that those of us who speak that language are able, by and large, to not only to recognize, but to agree upon. So it is, I think, a quality that is really there. It is not just a matter of aesthetic taste. And theoretical physicists look for beautiful equations, not out of mathematical aestheticism, but because it is proved to be the case that it is equations having that unmistakable character which also demonstrate, time and again, the long-term fruitfulness that persuades us that they are indeed describing the way the world is. I learned my quantum theory from the horse's mouth, so to speak. I went to the celebrated course of lectures given here in Cambridge by Paul Dirac for about 30 years, based very much on the content of his classic book, The Principles of Quantum Mechanics. And you probably all know the story that Dirac once said, "It is more important to have mathematical beauty in your equations than to have them fit experiment." So there. Now, of course, he didn't mean by that that empirical adequacy was something that a physicist could dispense with. I mean, obviously, at the end of the day, you really have to try and have some correlation with what's going on in the world. But what he meant by that, I think, was this, that if you have your new theory, you find that somehow or other the solution doesn't seem to correspond to the results the experimentalists are telling you about, well, that, of course, is a bit of a setback, no doubt, but at least there are some possible residual hopes of saving the day. Almost certainly you would have had to solve the equations in some sort of approximation, and maybe you didn't make the right approximation, so you have to go and reconsider that. It's possible that the experiments themselves are wrong. We've known that happen more than once, I have to say, in the history of physics. So at least there's some sort of residual hope that you might be able to save your theory. But if your equations are ugly, there's no hope. They couldn't possibly be right. The 300 or so year history of theoretical physics in its modern form testifies entirely against your being on the right track. And as you all know, Dirac made his very great discoveries by a relentless and highly successful quest for mathematical beauty. And of course that mathematical beauty, as I said earlier, paid out in terms of long-term fruitfulness. So Dirac comes along, he looks for a relativistic equation, combining quantum theory and special relativity. He looks for an elegant form of that. He finds the celebrated Dirac equation, which, by the way, if you don't know, is inscribed on his memorial slab in Westminster Abbey. If you go and have a look at that, you'll see that the Dirac equation is written on the slab. What the average tourist makes of that, I don't quite know. The irony of it isn't written in the notation that Dirac himself used. It's written, Dirac of course used the alpha and beta notation, which is not the most transparently relativistic notation. And there was a big debate, which I participated by correspondence, between the Dean of Westminster and a number of theoretical physicists about what form the equation should be written on the slab. I voted for Dirac's original formulation, unfamiliar though it would be to many younger theoretical physicists, but it's written in the gamma notation there, but there we are, that's the thing. Anyway, Dirac finds this equation. He immediately discovers that this equation, of course, explains the anomalous double diamagnetic ratio of the electron, but it's two rather than one, so to speak. That comes out of the equation as an uncovenanted blessing, you might say, and that's very impressive itself. And then, of course, he has the problems about the negative energy states. He doesn't find the best way of formulating the solution to that problem, but he finds the right way to recognize those as being interpretable in terms of the existence of antiparticles, and so antimatter comes onto the agenda. And here, of course, it's the nudge of theory that helps the experimentalists. In fact, experimentalists had seen positrons for a good few years before Dirac came along, but they hadn't recognized them for what they were. So there's a sort of cousinly interchange, or fraternal interchange, perhaps I should say closer than cousinly, fraternal interchange between experiment and theory in that sort of way. So mathematical beauty is a very important heuristic tool in theoretical physics. I mean, essentially Einstein found the equations of general relativity in a similar sort of way after a very long search, of course, 8-year search thinking about the nature of gravity. And I feel pretty sure that when he discovered those equations, he knew he'd got it. He'd cracked the thing. They were so convincing in their character, because he then had to go on and calculate the consequences for the orbit of Mercury. And he said it was the happiest day in his life when he found that the unexplained small discrepancy with Newtonian theory in the motion of the perihelion of Mercury was explained by his theory. So there's this sort of interchange. So the physical world has turned out to our inquiry to be rationally transparent. We're able to penetrate into its deepest secrets far away, whether they're in the subatomic world of quantum physics or whether they're in the cosmic realm of curved space-time. It's transparent to us, and it's also rationally beautiful. That the structures that we find when we enter these domains are ones that give us delight. And that, of course, explains the use of a word among physicists, which, of course, they never, ever use when they're writing their papers for the learned journals, but in my experience, they quite frequently do use in conversation, which is the word wonder. I've talked about understanding as the motivation for all the weary labor of doing research in physics, but wonder is the reward for that weary labor. It's that moment of illumination when something new and profoundly intellectually satisfying is revealed. Usually, of course, it's an experience of the community, the insight coming from some great insightful person who has discovered it, but it's then a shared delight among that community. So our experience of exploring the physical world, I'm talking about fundamental physics, not because I wish to be in any sense to be dismissive of more complex forms of physics. I mean, condensed matter physics and things of that nature. They have their beauties and their insights too, of course, but they're difficult. It's one of the reasons I became a particle physicist was it's much easier to think about 1 or 2 or 3 particles than to think about I don't know 10 to the 23 or whatever particles you have to think about. And so fundamental physics is pretty easy on the whole. Middle level physics from condensed matter upwards, or up, I suppose, up to astrophysics and things of that nature. It's pretty difficult. And good luck to those people who work in that area. And who again, of course, have produced very insightful understandings of what's going on. I mean, one of the very beautiful stories of astrophysics, it seems to me, in the second half of the 20th century was the unravelling, partly here in Cambridge through Fred Hoyle and then also through Willie Fowler, who was always toing and froing between Caltech and here, of the wonderful story of nucleogenesis within stars and within supernova explosions. I mean, it's a very, very beautiful chain of insight and discovery. So the physical world is transparent and rationally beautiful. You could summarize that, I suppose, by saying that it's a world who in its fundamental structure excuse me, seems shot through with science of mind. I would want to suggest that it's worth considering the possibility that it is indeed the capital M mind of the Creator that lies behind the rational order of the world. I know. That's not elderly gent, I like it. Just about managed.
More difficult than particle physics.
Sorry?
More difficult than particle physics.
Yes, I mean, it's not a knockdown argument for the existence of a divine mind behind the wonderful order of the world, but it's an intellectually satisfying explanation of it. It certainly seems to me incredibly lazy. It would be incredibly lazy just to shrug our shoulders and say, gee, that's the way the world just happens to be. A bit of good luck for you chaps who are good at maths. I mean, that seems to me to be neglecting something that is very deeply significant and calls for an explanation. If we're really serious about the search for understanding, if we're going to pursue that through and through, then I think we need to move beyond physics to metaphysics, to metascience, to have a broader and a deeper context, a broader, wider and a more profound story within which to locate the story that physics is able to tell. For my money, theistic belief provides actually, I think, the best explanation of the deep possibility of physics. I do believe actually that science is possible because the world is a creation and that we are creatures, to use an ancient and powerful phrase, creatures made in the image of our Creator. So I see our ability to do physics as a small part, but a very real and significant part of the Imago Dei, a gift that God gives to human creatures. And I suppose that thought is to some extent encouraged when you think about something about the history of modern science. The history of ideas is a tricky area, and it's very easy to read things into the story which are not necessarily there, and certainly it's impossible to demonstrate in some unequivocal way that the insights one's proposing are true, but nevertheless it's insightful. It's interesting to ask the question, why did modern science start in Western Europe in the 17th century, which is essentially where it began, in its recognizably modern form and continuous relationship to physics today. Why did it start there, rather than say among the ancient Greeks, who after all were very clever and curious people, or among the medieval Chinese, who in many ways were much in advance of medieval civilization in Europe? Well, it's impossible with certainty to answer questions of that nature, but it's possible to suggest, and it has been suggested, of course, and also contended against, that the Judeo-Christian Islamic notion of the world as a divine creation played an important ideologically supportive role in encouraging the birth of modern science. Because modern science involves, I suppose we see it starting with Galileo, where you get the fusion of mathematical argument. Galileo, of course, famously said that the mathematics is the language of nature. He said it was written in squares and triangles. It's written, I think, in a more extensive language than that, but that was a move in that direction. Mathematical insight and formulation of structure in that way with observation, and it's the putting the two together that really produced the fruitfulness of a modern scientific point of view. The ancient Greeks, of course, were very clever people And some of them, of course, were involved in empirical investigations. I mean, one thinks of Archimedes, one thinks of Hero of Alexandria. But by and large, they tend to place, under the influence of Plato and to a lesser extent perhaps of Aristotle, a great reliance upon the power of human thinking to penetrate in Platonic form, to penetrate the realm of ideas, the world of ideas, and to reach truth in that sort of way, in that sort of noetic access to truth. And so they didn't quite get on to the importance of empirical, of the nudge of nature in finding the ideas that we need. I'll say some more about that tomorrow when I talk about quantum theory. The Chinese were, of course, very clever people, but somehow or other, I may be wrong about this, but my impression is that they didn't really take the value of the non-human world sufficiently seriously to want to spend a lot of time and effort on its investigation. But when you have the doctrine of creation, it tells you various things. It tells you, first of all, that the world is God's creation, God is rational, so there will be an order to the world. That insight is correct. There will be an order to the world. So that, if you like, encourages the mathematical exploration of the possibilities of order. But it also says that the order that God has brought into the world is freely chosen by God. God is not, like the demiurge in Greek thought, is not subject to a blueprint already laid up in the world of ideas for the form that the creation has to take. God chooses the form of creation, so you have to look and see what particular form of order the divine will has settled upon. And that brings together this fusion of structural mathematical argument with observation. And of course it also says that if the world is God's creation, then it is a worthy object of study. And perhaps that's the bit that the Chinese may not have picked up, if I'm right, in my feelings about medieval Chinese culture. So I think there is a case. Not for saying that it was uniquely determined by a doctrine of creation, but that it was certainly encouraged and strengthened. And of course it's a simple fact that most of the great pioneers of modern science in that very early period were people to whom religion was significantly important. They may have had their difficulties with the ecclesiastical authorities, as of course notoriously Galileo did. It's a complicated story, of course. I mean, there were some faults on both sides there, I think. They may have had their difficulties with religious orthodoxy, as Newton certainly did. But nevertheless, they were people for whom religion was important. And most of the founding fellows of the Royal Society were people of religious convictions, many of them actually Puritans. So there is some sort of connection there, which is, I think, helpful to take note of. Well, I mean, singing the praise of physics and saying that it's wonderfully successful in its limited but valuable exploration, but of course it has its limitations. And one of the interesting and significant discoveries of 20th century physics was to discover that there are intrinsic limitations on predictability, for example. They came to birth, first of all, in quantum theory, notoriously probabilistic theory, so that we can't say for sure that this is going to happen, but we can say a certain probability of this, certain probability of that. And then it was a further surprise in the 60s to discover that even the macroscopic world, even the world of apparently classical Newtonian physics, was not as unproblematically predictable as people had tended to think. I mean, Poincaré had known that at the turn of the century, but that sort of got forgotten. But with the discovery of chaos theory, essentially coming through computational investigations of simple nonlinear equations, showed that exquisite sensitivity to the fine detail of circumstances meant that there are many systems in the world which are clouds rather than clocks, whose future behavior may be constrained, but is not predictable in that sense. So the discovery of intrinsic unpredictabilities in the world was a very important and significant development. What you made of that? Well, first thing that I think unequivocally you can make of that is that the physical world is certainly not merely mechanical. That is to say, tame, controllable, predictable. I mean, that had very much seemed to be the aftermath of Newtonian discoveries. Newton himself didn't take a mechanical view, merely mechanical view of the world, but his successors certainly did, particularly in France, and that wasn't really changed by Maxwell's exploitation of field theory in the 19th century. The world did seem to be quasi-mechanical in its character, but that is certainly clearly not the case. What you make of unpredictabilities is something that is not settled by physics alone. And that's here again we bump into another limitation of physics. Questions of causality are, of course, constrained by what physics has to say, but they are not completely determined by what physics has to say. Contrary to what many people out there, I think, would tend to suppose. And of course, quantum theory makes the point. Unpredictabilities can essentially have two different sources. They may arise simply from ignorance. Ignorance of fine detail, ignorance of the complete panoply of causal principles that are actually at work to determine what's going to happen. There may be intrinsic unpredictability. Of course, the word intrinsic is very important here. We're not talking about unpredictabilities that could be resolved by more exact calculation, more precise measurement. We're talking about intrinsic unpredictability. They may arise from just necessary ignorance of what's going on. Or they may, of course, arise from a more fundamental reason there, simply from intrinsic indeterminism present in the system. And I'm sure you know that quantum theory, notoriously unpredictable in that detailed sense, and notoriously probabilistic, can be interpreted in either way. The conventional interpretation, which goes back to Niels Bohr, well, actually goes back to Max Born, but was sort of part of the great sort of Bohr tradition, interprets quantum theory as indeterministic. But that's not in an intrinsic sense. But that's not inevitable. That very clever man David Bohm came along in the 50s and showed that you could have a deterministic theory that gave exactly the same experimental results as conventional quantum mechanics, where the unpredictability arose from a necessary absence of knowledge of all the causal factors that were involved. Some of you will know about Bohm's theory, perhaps not all of you will. It's a clever trick, really. I mean, he does it by essentially divorcing wave and particle. I mean, in conventional quantum mechanics, wave and particle are complementary aspects of a single entity. But in Bohm's theory, they are both particles and a hidden wave. The particles are as unproblematically objective as Isaac Newton would have wished them to be, but there is this hidden wave that encapsulates information about the whole system. It's a holistic information carrying system, and it influences the motion of the particles. And Bohm put the two together in such a clever way that he was able to obtain the same experimental results. So physics itself cannot tell you the difference between necessary ignorance or indeterminism. That is a matter of metaphysical decision and has to be made on the grounds of the metaphysical criteria. Most of us, I'm with the conventional majority on this point, most of us sign up with an indeterministic interpretation of quantum mechanics, basically because I think we think that Bohr's theory is clever, Bohm's theory is clever, but it's too clever by half. It has an air of contrivance about it. I don't want to spend too much time talking about this, but of course Bohm has a wave, so he has to have a wave equation. What's the wave equation? Well, you won't be surprised to know, if you don't know already, that the wave equation is the Schrödinger equation. And why is it the Schrödinger equation? Because he won't get the right answers unless it is the Schrödinger equation. And where did he get the Schrödinger equation from? Of course, he got it from Schrödinger. So it doesn't have quite the sort of natural inevitability that one would like to see in a fundamental physical theory. There are other objections too, which we could go into if we wanted to. So there are limitations to scientific understanding. We'll talk a bit tomorrow about temporality, and similar issues will arise, I think, in relation to that. So physics constrains metaphysics, constrains the general principles of the reality in which we live, but it doesn't determine them. Rather in the way that the foundations of a house constrain what you can erect upon it, but don't determine the nature of the actual edifice. So that's a limitation that's present there in physics. The other thing, it seems to me, is that our knowledge of physical world, though it is very good, is also patchy. We have certain well-known regimes that have been well explored, and we can make theories which essentially correspond to very accurate and impressive maps of that particular domain, to use that a cartographical metaphor. No map, of course, contains all the detail of a domain, but it contains the essential features for a particular purpose. And the maps that physics is able to make can be astonishingly accurate. I'm sure, just let me remind you that quantum electrodynamics, the quantum electrodynamics calculations of the anomalous magnetic moment of the electron, agree with the experiment to an accuracy which corresponds to a discrepancy no more than the width of a human hair in relation to the distance between Los Angeles and New York. That's a pretty impressive form of accuracy. So they do it very well. But we don't know how to superpose the different maps. We don't know how to put together the subatomic quantum world, its map and its understanding, with, for example, the world of macroscopic experience, of microscopic classical physics, or classical-like physics. I'll say more about that tomorrow, but just let me give you one today, a couple of examples of that. One is the relationship between chaos theory, macroscopic unpredictability, intrinsic unpredictability, and quantum theory, microscopic intrinsic unpredictability. Very soon, if you quite simple chaotic systems, just collections of colliding billion balls and so on, will soon come to depend on fine detail at a level of accuracy that actually Heisenberg's uncertainty principle forbids us to have access to. So you might say, okay, well, let's put together chaos theory and quantum theory, let's knit the two together, and then we'll have a sort of single open indeterministic kind of theory. And that'll be a good thing to have. But we can't do that. Quantum chaology, as people call that attempt to fusion, is something that is not consistently attainable. And the reason for that is very simple. Of course, quantum theory is a theory that has a scale, essentially a scale set by Planck's constant, whilst we all know that chaotic systems behave in a fractal-like character, and fractals, of course, have no scale. They are the same all the way down. And you can't obviously meld together a theory with a scale and a scale three theory. So there is an ununderstood connection between the two. Our knowledge of the physical world is distinctly patchy, and claims, for example, that I mean, it's absurd to think that a subatomic theory, like, let us say, string theory, if string theory really turns out to be what the world is like, I'm very doubtful of that myself, but if it does turn out to be true, to call it a theory of everything is an absurdly bombastic and hubristic way of talking. I mean, suppose string theory is absolutely right, and don't forget, of course, that string theorists are claiming to be able to second-guess nature 16 orders of magnitude, at least 16 orders of magnitude smaller than anything which we have direct experimental contact. And the history of physics is not encouraging such ambitious feats of human imagination. But even if it were true, it wouldn't really help very much with explaining the turbulent behavior of fluids, for example. I mean, theories of everything are beyond our grasp in any true sense of that meaning. And I believe there are difficulties. Another example of the level differences is how to relate continuum mechanics to molecular physics, because I understand that the eddies in turbulent motion can be essentially of molecular size, and so you have a difficulty of joining up there. So physics is possible, but it's not without its problems and not without its limitations. Not only the intrinsic limitations of what it's prepared to consider by way of empirical experience and what questions it is prepared to ask of that experience, but also within itself in not being able to give an exhaustive account of everything. There are inescapable gaps in it. I don't say that in any sort of sense of rejoicing, and certainly not to belittle physics, but one has to recognise the reality of the situation. I've almost said what I want to say, actually, which is a bit too quick. I'm sorry about that, but perhaps you may be relieved about that in some ways too. Sometimes people ask me, I was in physics about 25 years, and then people say, well, did you get disillusioned with physics? And I often say, absolutely not. I was very glad to be a physicist, use such modest talents that I had in that direction. I enjoyed being part of a very vibrant and successful physics community, the particle physics community, and it was a great fun. I've tried to keep a continuing interest, of course, from the sidelines. Now my old subject is developing. I mean, I can see the drift of string theory, though I couldn't write down all the detailed equations of a heterotic superstring or something like that. So I retained an interest in physics. I didn't leave physics because I was disillusioned with it. I left physics because I thought I'd done my little bit for it. And here's a word of warning. If you're a theoretical physicist, it may not be true of experimental, I'm not quite sure, but if you're a theoretical physicist, in these mathematically based subjects, you don't get better as you get older. What counts is not experience and wisdom and that sort of thing, it's mental flexibility. And the sad fact is that you lose mental flexibility as you get older. You can do the old tricks, but it becomes harder and harder to do the new tricks. It's unlike, on the whole, most people in mathematically based subjects, I don't think, do their best work before they're 25, though it's a sort of conventional thing to say that's what they do. I don't think for most people that's true, but almost for all of us, it's true that we've done our best work by the time we're 45. So, look out. And I see from very respected senior colleagues of mine who stayed around, get a little miserable, really, I think, as the subject in some sense moved away from them. And I just felt that on my bit, I would do something else. So I didn't leave physics because I was disillusioned with it. I think it was a worthwhile thing to do. I felt I had a vocation to do that. And of course, for good or ill, that's no doubt a bit mixture of both, I retain the habits of thought of a physicist. I like to think of myself, sometimes to speak of myself as being two-eyed. I look at the world through the eye of science, I look at the world through the eye of religion. And I believe that that binocular vision enables me to see more clearly and more deeply and more accurately than I would with either eye on its own. So the possibility of physics is a remarkable fact. It's a theologically explicable fact if you believe the world to be a creation. It seems to me it's a somewhat puzzling fact if you don't have some such view as that. But that's what I think. And perhaps you'd like to tell me what you think. So over to you, Rick.
Well, thank you, John. One of our aims of having a limited number of people is so we can interact. We always have allowed plenty of time for questions, and we have got plenty of time tonight.
Yeah, I'm sorry about that. Yeah.
Oh, we got plenty anyway. So it'd be great if people want to reflect on anything John said or ask questions directly about it.
Okay, so you were talking about why it's possible to do physics, and a lot of the argument seems to be also applicable to the question why it's possible to do science.
Yeah.
So specifically, what's special about physics that allows us to do it? For example, it is patchy. It's patchy because we've got constants that separate out various scales. So you can do molecular dynamics, you can do continuum mechanics.
Right.
The theories don't necessarily need to talk to each other that much. Is it that makes physics possible, specifically for physics, or are there other things?
Well, I think a number of things make physics possible. One is that in some sense it's the simplest of the sciences. and I think I've said somewhere this evening, I can't remember where I said it now, that elementary particle physics is the simplest of the branches of physics because it deals with small numbers of things. So physics tends, even complicated things like theories of superconductivity and things of that nature, compared with biological systems, are dealing with matters that are more tractable and so on. So that's one thing about physics. Makes it a little bit different. I mean, most of the things I've said, apart from the role of mathematics, do seem to be fairly common to science. Many sciences use mathematics, but in the mode of using mathematics as a heuristic tool to actually discover new kinds of theory, that does seem to me rather specific to physics, and physics has this marvelous language, as Galileo insisted, and which physicists have been exploiting ever since. So those would be some of the respects in which it seems to me physics is a little bit different. Of course, there are gradations in all these things, and of course it's the extremes of physics which are the easy bits, the very small or the very large. Again, because of essentially you don't have a multitude of scales, overlapping scales. You have a controlling scale usually in these things.
Perhaps I can ask some. I think it was Lord Rutherford who said, wasn't it, that there's physics and everything else is stamp collecting.
Yes.
Is that your view as well?
No,
biology is immensely complicated, but is it just that physics will one day catch up with biology, or not? I know there's people in this room that are physical biologists or biological physicists, like Ard and so on. What's your view on that?
Well, Rutherford was an amazing character, and a very bluff sort of chap who doesn't hesitate to express his opinions about things. And when he talked about physics, I think he essentially meant experimental physics too. He wasn't, I think, too enamoured of theorists. Though when he did those experiments on scattering of alpha particles off gold foils, he was able to sit down and use his old mechanics textbook from New Zealand to figure out about wide-angle scattering from point sources. So Rutherford had a particular view and a particular way of expressing himself. I think it's amusing among physicists to say that, but I think it's extraordinarily dismissive to say that. If you ask yourself, what scientist has most influenced human thought and understanding about the general character of the world in which we live, my answer to that would not be Newton, great man though he was, or any of the pioneers of quantum theory, but would be Charles Darwin. Evolutionary insight and the importance of history and the irreplaceable role of historical development. So that you have to understand the past in order to understand the present. That seems to me extraordinarily powerful and insightful thing, which has influenced human thinking in very wide ways, more than any discovery in physics has done. So if it's all the rest of stamp collecting, there's some pretty remarkable stamps that they're able to collect. I think. I think physics imperialism is something to be resisted. Really, it's you can get carried away with it.
Yes.
Paul Davies, in his most recent book, The Goldilocks Enigmas, a statement about the history of life, and he says something like, to sum it up in a single phrase, it's 1% physics and 99% history. But in the context of that, so we have 4.5 billion years of history, the evolution of life on Earth. To what extent would you, is it possible that we can ultimately just reduce this to extensions of the laws of physics, or is there something else that is needed to understand evolution?
Well, evolutionary insight, broadly interpreted, involves, as in the slogan phrase, the interplay between chance and necessity. And chance stands for not for the goddess Fortuna in a capricious mood, but for contingency, in other words, for the role of particular historical developments. And that's obviously a very important part of it. I mean, it clearly wasn't laid down from the foundation of the world that Homo sapiens with 5 fingers should appear upon the scene at some stage. But biologists have tended, particularly those inclined to write quasi-philosophical remarks about biology, have tended to emphasize the contingency side very much to the exclusion of the necessity side. And two things make it perfectly clear, I think, that it isn't even balanced between the two. One, of course, is all the argument of the anthropic principle. There's a sense in which the given physical fabric of the world, of this universe, shortly after the Big Bang, had to take essentially its finely tuned form for the production of carbon to be possible, and therefore a carbon-based life, and so on and so on. We all know that story. So the necessity side of it is an indispensable thing. You could have if you just alter the laws of nuclear physics a little bit, you could have a universe that, as far as we can figure out, could have evolved away as much as it liked. So it has as much contingent exploration as possible, would never have brought to being such interesting consequences, certainly as carbon-based life. So that we shouldn't underplay the necessity side of things. And physics, of course, has a lot to say about that. I mean, not exclusively, but most of the anthropic insights are essentially derived from physics. And then, of course, we also have the very interesting sorts of things that Simon Conway Morris is saying here in Cambridge about convergence in evolution, the way in which similar structures have appeared many times. You get many independent acts of evolution of the eye. There are commonalities between them, and sometimes there are very close commonalities between the cephalopod eye and the human, and the mammalian eye, and so on. So that what Conway Morris is essentially saying is that possibility space is not this vast setting of random walk exploration that people like Dennis and so on want to say, but that it is actually quite tightly constrained. Possibility, the number of biologically accessible and functionally effective structures is probably much smaller than we think, and part of that is obviously constrained again by physical possibilities. So the whole story is not. I think 1% physics and 95% the rest is a little bit undervaluing our subject in relation to that.
But just to pick up on what Simon Conway Morris said, I think he did say something slightly different from you because of that convergent evolution. He said, in his view, I think he says this in his book, something like Homo sapiens, something like us, would have arisen anyway, and if we replayed the tape of life, it would arise again anyway. We would arise.
I don't think he says a 5-finger.
I don't know about the 5 fingers as opposed to 4. But
no, he does say it, and I think that Simon, of course, likes to make provocative remarks.
Indeed.
I think we have to remember. He does say that he thinks that if there are extraterrestrial life, it would be more like us than we might suppose. But I don't think for a minute that it's a happy accident that self-conscious beings of our degree of complexity have appeared on the cosmic scene. I think that really was a possibility, a likelihood built in there from the start, and I think that reflects actually the purpose of a creator. But there will obviously be lots of contingent things about the precise form of that.
Yeah. Should we take one from you?
Does that also mean that you expect that there are life on many other places in the universe? If the universe is designed, say, in a way for that reason, then there's no reason why it should be restricted only on Earth.
Well, that's a very interesting question. I don't think we know the answer to that, either scientifically or theologically. Scientifically, there's lots of arguments that, of course, obviously, if you're going to have life develop, you've got to have the right chemical composition, right temperature, and that sort of thing. People suggest that there are lots of other factors that may be also of critical importance, like, for example, the Earth has an enormously large satellite in the Moon that helped to stabilize the rotation of the Earth and also produce strong tides that scoured mineral material from the surface of the Earth into the oceans where maybe life developed. So it may be that the sites in which life is able to develop are quite tightly constrained. But if you've got 10 to 22 stars, most of which have planets, it would be very surprising if there were really rather a lot of suitable sites. What we don't know, it seems to me, is how easy it is for life to develop given all the necessary circumstances. And there are very great experts who just disagree about that. I mean, Francis Crick, with panspermia and all that, thought it so difficult to think that life understand how life had come about once. He couldn't imagine it happening twice. And certainly Francis didn't have any covert religious agenda in what he said. You get somebody like Christian de Duve, another Nobel Prize winner, comes along and says, yeah, apparently it happened way later years, it's a certainty. Well, I don't, you and I, as physicists, when the great experts of biology disagree, I think we conclude they don't know the answer. So I think scientifically we don't know, because we don't know how easy it is.
Theological argument. You bring in a theological argument that there is some sort of, you believe that also life is a gift from God to the world, to the universe.
Well, I've spoken about the theology. I'll say a word about that.
No, I think you said that it is not purely contingent.
Well, I think it is. I think it is not a happy accident myself that the circumstances of the universe are such that allow the development of carbon-based life, and I think that the size and age of the universe is such as to encourage the possibility of being supportive of the possibility of life turning up somewhere, as we know, in fact, because it has. But what I don't know is whether that will happen many times. And theologically, the discussion about that is actually quite old. It started really when Galileo established that, most people's satisfaction, that the planets are made out of the same substance as the Earth. There isn't a quintessence out of which the heavenly bodies are made. And people began immediately to ask the question, are the Venusians or the Martians? And did Christ die for the Venusians, and did Christ die for the Martians? So the theological argument began there. And essentially there were two theological answers given to that. One was that to redeem the whole of creation, it is sufficient that the Word of God should take creaturely nature once. That will do the trick for everybody. And there is a certain theological logic in that, but it seems a bit hard on the little green men if they don't know about it. So there's an alternative view, which one I would take if I were forced to take sides on this issue, which says that if there are little green men in need of redemption, then the Word will take little green flesh as the Word took our flesh for our redemption. And it says that it is not incoherent to believe that there could be incarnations in different kinds of rational beings. Though I think most of us would think it is incoherent that there should be more than one incarnation in human nature. So those were the options, and obviously the argument goes to and fro about that. But I think theologians would be wise, and indeed religious believers generally, would be wise not to limit the creative generosity of God, but suppose that God's purposes are simply fulfilled. So the genus Homo.
Rodney.
I wonder, we'll probably come back to this later on with other speakers over the weekend, but I wonder whether you think we're moving back towards a Platonic way of doing physics when it comes to some of the more fundamental issues such as string theory, and people are talking about there being a crisis in physics and at the moment.
Well, can you just unpack what you mean?
Well, string theory is this candidate for the ultimate theory of everything, which we've already been told is a terrible misnomer, and yet it doesn't seem to predict anything. It's pure mathematics without any experimental backup, and indeed it's 16 orders of magnitude away from that possibility. So are we back in this Platonic realm of trying to do things by pure thought?
Well, that's an interesting point, Rodney. I mean, something very odd, I have to say, something very odd has been happening in my sort of theoretical physics since I left it, but there's no connection between those two statements. I've said already that all the time I was in the game, it was experimentally driven, and that's what led theorists to the so-called standard model, the quark structure of matter, quantum chromodynamics, and all that. That was, I think, a pretty healthy state of affairs, but that was established essentially by the middle 70s. Since then, I mean, two things have happened. One is that the amount of experimental input into the subject has decreased. These accelerating machines are extraordinarily expensive to build. The taxpayer is impatient about providing the money. They take a long time to build. And so it hasn't completely dried up. And of course, when the LHC, the Large Hadron Collider, comes on stream at CERN possibly this year or next year, then a new energy regime will be explored, and people hope that we'll find the Higgs particle, maybe supersymmetric particles and things of that nature. So it hasn't dried up completely, but it is, unless the accelerator physicists have a tremendously good new idea, it is going to dry up in the not too distant future. I mean, you can't. Precision engineering on 10 kilometer scales is one thing, on 100,000 or 1,000 kilometer scales is a different matter altogether. It's not going to happen. So the experimental input has dried up, and at the same time, and perhaps connected with that, there has to develop this extraordinary degree of speculative self-confidence in the theoretical community. That they really think that by thinking hard, it's a Platonic venture in a way, that by thinking hard, they can figure out what to do. And of course, as you know, string theory at the moment is subject to a bit of an onslaught from people. I mean, for a long time it's been the only game in town, all the best people work in it, but it's now, whatever it is, well, more than 20. How you date its beginning is one of these contentious things, but certainly 20 to 25 years old, and it hasn't produced any empirical, verifiable consequences. And it hasn't really paid off even on its theoretical bill of sale in the first place. The hope was that string theories would either be unique or almost unique. And now we have the landscape, we have the realization that when it comes down to actual physical consequences, they're fantastically far from unique. People estimate there are 10 to the 500, pretty big number really, 10 to the 500 different possible sets of consequences for string theory. And in the present mood, some people don't hesitate to say, therefore, there are 10 to the 500 different universes. Now that doesn't seem to me to be science, I have to say. It does seem to be rash. I think it's very bad for really bad for physics. I mean, it's very sensible that clever people, and of course there are some enormously clever people involved in this enterprise, the clever people spend significant amounts of time exploring the richness of relativistic quantum theory. We know that that's a very rich theory, richer than either theory would suggest on its own. And to explore that in terms of fundamental entities that aren't points but are strings or whatever, it's an interesting exercise and a worthwhile exercise to know what the options are. But to think that that is necessarily describing what the physical world is like, that it is a theory of everything in any sort of sense, is to go far beyond justification. And the fact that it has become the only game in town, I mean, there's these books that list, all the leading physics universities and all the theorist departments are dominated by string theorists. That is, I think, a very, very happy state of affairs. Yeah.
As an experimental particle physicist, I think I need to protest just a little bit. Over the past 25 years, of course, there have been a lot of activity in many accelerators in many parts of the world. Huge numbers of papers, huge numbers of experimental results. But what is significant is that the standard model has been so successful that the experiment has simply just confirmed the predictions of the standard model of particle physics pretty well all the time. There have been a few sort of indications in other directions which are very interesting, like masses of neutrinos. Yeah. But that's the real thing, that the experiments haven't discovered things that have forced the theorists to think along new lines. And that, I think, is what our speaker was really trying to get at.
Yes, okay, yeah. I mean, I gave a rather sort of crude, broad brush account of things. I was comparing it really in my mind, of course, with the era that I lived through, where the experimentalists were producing every Rochester conference. There was a sort of sensation of one sort or another, which I mean really did drive theory in some new directions. And that was of course a sort of frenetic, enjoyable period that couldn't last forever. And I mean, I'm all in favour of experimentalists. Very broad-minded chap. Andrew.
You talked a bit about the, if I can use short.
Can you hear it back? Stand up,
Do you want me to stand up here?
Yeah, turn the front.
Yeah.
so-
Yeah.
To use shorthand,
Turn this way.
the theological driver of science and of physics, that
Yeah.
the belief in the dignity of, or its, that the world is created makes
Right,
you want
yeah.
to understand it. And I was wondering whether how much one can say about the relationship of that to the technological drivers of science. You mentioned that Charles Darwin might come top of the list for the person who's most changed the way we think. And one could have, I suppose, an interesting debate over drinks later on as to whether his work has had the same impact on our technology as someone like Maxwell's work has
Well,
had.
of course, yeah.
But there have been technological drivers of science as well as intellectual and theological drivers. Or to put it another way around, one could ask not only why is mathematics so successful for understanding science, but why is science so successful for enabling us to develop technology and change the way we live? Now, is that a trivial question that just has a trivial answer, or is there something deep about this relationship between the theological and the technological drivers?
Well, thank you. I mean, I've been very much giving a pure science point of view, and that's my sort of context, I suppose. Of course, I mean, there is a very important interface between pure science and technology. A lot of developments in pure science, for example, are enabled by developments in technology. I mean, the big accelerating machines need all sorts of clever control devices and spin-locking magnets and all that sort of thing. So it is a two-way trade. The way I see it is that it seems to me that pure science gives one knowledge, and that it seems to me always a worthwhile thing to have. It seems to me knowledge is always better than ignorance, whatever one's thinking about. And technology uses that knowledge to get things done in ways that, of course, we all benefit from enormously, in all sorts of ways. And that's where a lot of the problems come in, because, of course, once you move into that practical realm of getting things done, of technological possibilities, not everything can be done, should be done. And that's where many contemporary ethical problems in relation to science arise, particularly, of course, these days, I think at the present time, in relation to genetic sciences, which are developing so rapidly. Therefore, you have knowledge and you have power, which technology gives us. But as far as society is concerned, and the broader settings, you have to also acquire some gift of wisdom, which is the ability to discern the good and accept it, to discern the bad and refuse it. And so the technology is extraordinarily important, but an ambiguous gift in that sense. There must be examples, perhaps, where technological desire may have pushed more pure scientists to investigate phenomena a bit more. I can't on the spur of the moment think of a very good example of that, but perhaps you could suggest one. But of course, there is a trade across the board.
Like nanotechnology, for example.
Yeah, well, yeah.
It's a name of one.
Yeah, you talked about the relationship between chaos theory and quantum theory. Both are essentially not deterministic theory, and is quite good in countering the arguments that science can explain everything, particularly the Laplace
Can
kingdom.
you speak up a bit?
Yeah. You talked briefly about the relationship between chaos theory and quantum theory,
Yes,
which are essentially not deterministic theory and actually counters the argument that everything can be explained through science, the arguments of Laplace and all. But in trying to marry the two, in the sense like to see the relationship between the two, we did talk a little bit about the scales issue, but probably you're going to talk more tomorrow. But one of the things which occurred to me was that chaos or nonlinear dynamics is essentially an irreversible process, and quantum theory is a reversible phenomenon because of the unitary evolution incorporated. So I thought I would like to just...
That's obviously true. Yeah, so that's an illustration of how things get complicated when they get out of the simple realm of things like particle physics. Yeah. Go on.
Just speaking on chaos and quantum theory, I'm curious as to what sense you mean you can't. well, marry the two. I mean, I can understand that if quantum theory is correct, of course, there is a scale. And so chaos theory with the fractals doesn't really apply to all scales. But I mean, I would have thought that fundamentally we should just do the quantum understanding and that's it. And there's no fundamental problem there. It's just the chaos, there's a limitation to chaos theory because it doesn't apply when the action gets below the Planck scale.
Yes, but I mean, you see, we don't understand. I mean, I gave that as I thought to be a fairly simple example. In fact, we don't really understand the transition between quantum physics and classical physics. The measurement problem in quantum theory I'll say something about tomorrow is another example of that. We don't understand how the apparently reliable, steady world of every day arises out of this cloudy, fitful quantum substrate. And the fact that, and I was just using the mismatch between chaos theory and also, I mean, the quantum picture, of course. But perhaps I'll say more about that tomorrow. I'll tell you a bit about decoherence tomorrow, which is another important issue. Yeah.
I just wanted to follow on to that. So, I still don't quite understand this connection. But let's take one example, which is like you can take highly excited Rydberg states, and they will eventually go over into something which has some kind of quantum chaos behaviors. We're blocking to study quantum chaos. So what you would say is, okay, why is quantum chaos? As you move up in the correspondence principle, at some point you can start describing things reasonably well by classical equations. Okay, and eventually those classical equations will start developing what we call chaos. So it's only above those scales that chaotic dynamics and all those kinds of self-similarity arguments hold. We know that they don't, and so I'm sure I'm misunderstanding what you're trying to say, because
well, I think what I'm
fairly straightforward.
What I'm trying to say is that correspondence principles are not as unproblematic as you're suggesting. I mean, the zero-order approximation of thinking about these sort of things is here's quantum theory. As you say, things get a bit bigger, it all turns into classical mechanics, and we have correspondence principles that show that there are relationships between the classical results and the quantum results. But there isn't a single separating scale that enables that transition. The border between quantum physics and classical physics is fractal-like. There is interpenetration between the two, and that's the bit that so that once you get systems that are more complicated than, say, atomic energy levels, which is where, of course, correspondence principles were initially exploited in quantum theory, then it's not so unproblematic. You don't get it's much more subtle than people realized at that time. That's basically the problem.
But so, there's a large literature on people studying exactly this problem in atomic physics because it's interesting, right? Because it shows this.
Well, I'm sure my understanding, because I have to, my understanding is not very great. It derives from talking to people like Michael Berry and so on. It is just drop a name or two. Keep my end up. It is that there are still lots of very unresolved problems in that respect. People are working on it, and it's very good that they are, and I'm sure that they're gaining understanding. But it is not. I mean, I would guess that if you were discussing this problem in 1930, you would have said exactly what you say, that the correspondence principles, it all just emerges in a fairly unproblematic way. But it doesn't seem to work that way, as I understand. Is that right?
Yeah, I agree. Well, one of the problems is the conceptual mismatch.
Yeah. Yes.
So you've got two theories which are conceptually different, and you just can't glue over the.
Yeah.
Is there anything that you see with your eye of science that conflicts with your eye of religion?
Well, I've never felt that. I mean, there are of course puzzles.
Dawkins. Dawkins is the puzzle. He's very existent.
There are puzzles. I mean, there are all sorts of puzzles. I mean, there are all sorts of puzzles of exactly on this how our experiences as I mean, there are all sorts of puzzles, not only at the religious level, but at just the general sort of everyday level, of how our experiences as agents relate to fundamental physical processes. We're embodied beings. exactly how that works out, we don't understand. So there are lots of puzzles, but I've never felt a crisis situation. I've never felt that I had to face the choice between science or religion. I've always seen them as being complementary related to each other, as friends and not foes in that respect. That's my personal history.
Can I come back to you? Can you think of areas where they might be in conflict?
What about the problem of evil, John?
Do you have any?
Well, Chris says one about the problem of evil.
Take that one first, okay?
Yeah,
we'll do the easy things.
Well,
first.
that's an interesting.
We'll do the easy things first.
That's right, yeah. Actually, that's a very interesting example, I think, of how scientific insight actually, in a small way, is helpful to theological thinking. You know, I mean, there's this sort of caricature picture that 1859 Darwin published The Origin of Species. All the scientific chaps shout yes, yes, yes. All the religious people, especially of course the obscurantist clergy, shout no, no, no. That's the big party of the ways. Of course, it was much more complicated than that. There were doubts on the scientific side. Where did these small variations come from? Until Mendel's discoveries were rediscovered. Genetics, that was an unsolved scientific problem. And on the religious side, there were people who welcomed Darwin's insights. Most notably, people like Charles Kingsley and Frederick Temple in this country, and Asa Gray in North America. And Kingsley coined the phrase within a year or two of the publication of The Origin, which I think perfectly encapsulates how to think theologically about an evolving world. He said, no doubt God could have snapped the divine fingers and brought into being a ready-made world, but God had in fact done something cleverer than that, bringing into being a world so endowed with potentiality that creatures could make themselves. The shuffling explorations of evolutionary process were bringing to birth, in contingent ways, the fruitfulness of which the Creator had endowed creation. That's a very positive view of the world, and I think myself, if one may venture to use that language, that a creation of that sort is a more fitting creation than a ready-made world would have been. It's a more fitting creation for God of love, who is not the cosmic puppeteer pulling every string, but allows creatures to be themselves, indeed to make themselves. So that's a positive reaction, and that is, I mean, of course, very much explored in all sorts of ways by my friend and colleague, the late Arthur Peacock, for example, talking about evolutionary theory and continuous creation. So I would say that a world in which creatures make themselves is a better world, a greater good than a world in which is ready-made. But it has a necessary shadow side, because the shuffling explorations of contingency will also have blind alleys and ragged edges. And there is an ambiguity about it. Biological evolution has been driven by genetic mutation in germ cells, producing new forms of life, which then simply by natural selection. But if germ cells are to mutate, then of course somatic cells will also be able to mutate, and they will sometimes become malignant. So the fact that there's cancer in the world, which is an anguishing fact about the world, and not something I'm trying to say is trivially disposed by what I'm going to say, but at least you see it as the necessary cost of a world in which creatures make themselves. It is not something gratuitous that a God who is a bit more competent or a bit less callous could easily have eliminated. Now you can argue whether it's a proper cost to pay for the fruitfulness of the world, but there is some help there, I think, as theology wrestles with problems of evil and suffering, which I think are the most difficult problems of religious belief. Hold more people back from religious beliefs than anything else, trouble those of us who are believers more than anything else. But it is mildly helpful in that area, and that's a gift from science, I think, which is really to be gratefully accepted. And that's, of course, the irony, really, of the people who resist Darwinian insights.
Do you want to come back with any other?
Well, I just wonder how science and scientific discoveries affect how we should speak of God, how we can talk about God. Because the scriptural portrayal of God is so different from scientific language, and yet we can merge the two disciplines in some areas. But doesn't that affect how God should be presented?
Yes, yes. I think those of us who are, again, for good or ill, are a part of the scientific community have certain habits of thought. And I see a cousinly relationship between science and theology to some extent. In fact, here comes the commercial. Our most recently published book, published about 2 or 3 months ago, is called Quantum Physics and Theology, and it's not. It's a book with a single thesis. The thesis is that, of course, the two subjects are very different in their subject matter, but if you look at their rational schemes of argument and heuristic devices, you strip bare what's going on in the two, I think we can discern a cousinly relationship. And I have 14 different paired examples of that to try and make the point. You see, I mean, I've got a lot of friends in the scientific world who are both wistful and wary about religion. They're wistful because they can see that science doesn't tell you everything. They want a broader and a deeper story. But they're wary of religion because their picture of religion is that religion is based on unquestionable submission to authority. Faith, they believe, is shutting your eyes, gritting your teeth, believing 6 impossible things before breakfast because somebody tells you that's what you've got to do. And they don't want to commit intellectual suicide, and neither do you and neither do I. So what I'm always trying to say to my friends is that I have motivations for my religious beliefs, just as I have motivations for my scientific beliefs. Of course, there are different kinds of motivation because there are different kinds of belief. I mean, any form of personal knowledge and understanding will have to find a role for the unique, while science is essentially based on repeatability. Now, there are differences between them, but both in science and religion, I believe we are searching for truth through motivated belief. And I think in neither of them do we obtain absolute certainty, but we obtain sufficient understanding to commit ourselves to what we believe to be true. My favourite philosopher of science is Michael Polanyi, and in his great book, Personal Knowledge, he says in the preface, I'm writing this book, and he's talking about science, remember, I'm writing this book to show how I may commit myself to what I believe to be true, knowing that it might be false. And that, I think, is the human condition, actually. So I think that's why I think there's a sort of cousinly relationship. And to me, the Bible is not a sort of textbook with where you can look up all the answers. Its authority, I think, comes from the fact that it is the irreplaceable record of God's acts of self-disclosure through the history of Israel and through the life, death, and resurrection of Jesus Christ. We wouldn't know about those things, essentially, if we didn't have the Hebrew Scriptures and the New Testament. And that's where their authority derives from. They are, in some sense, laboratory books of the divine self-disclosure. That's how I see it.
Thank you. There was a question at the back which I missed earlier.
Anybody prepared to own up at the back?
I think we'll just spend a few more minutes and then we've worked on very hard. But do you want to come back with it?
Sorry, I'll stand up.
Yeah.
One last question, just to clarify on something you said at the very, very beginning.
Right.
Which was talking about the remarkable, the way that there's 2 things I think you're trying to say. I just wanted if you could unpack the difference a little bit. One was the idea that it's amazing that we can understand the world because mathematics allows us to understand it. The other one was it's amazing that we humans have somehow evolved this ability to understand the world.
Yes.
And I wondered whether you could, I can easily see where someone might say, well, our ability to understand mathematics is simply a byproduct of all kinds of other, obviously somebody who's very clever who is more clever than the people around them will survive better, and as a byproduct they can also understand mathematics, just like they can understand literature or language.
Well, actually, I don't believe that. I think that our ability, our mathematical ability, is another feature of human nature that goes beyond simple evolutionary explanation in classically pure Darwinian terms. If the context of human evolution is simply the physical-biological context that conventional Darwinian theory is, I think it's very hard to understand where deep human mathematical ability comes from. Of course, it's obviously useful to be able to count, it's obviously useful to have notions of Euclidean geometry, but what's the point of non-commutative algebras, of the ability to prove Fermat's last theorem? Again, it seems to me our mathematical abilities greatly exceed anything that is susceptible to honest evolutionary explanation. Now, at least in Darwinian terms, now, evolutionary explanation depends upon getting not only the genetics right, but getting the ecology right, the context in which it takes place. And I myself think, I'm a Platonist about mathematics, and I think that there is a noetic realm of mathematical reality, and that when our ancestors first began to develop minor mathematical abilities like counting and some notion of properties of space, that began to give them access to that realm, and that they were then drawn into an ever-enhancing experience of exploration in that realm, not driven by survival necessity anymore, but driven by something you might call intellectual satisfaction. I think that's what. So I think I think it's very hard to understand the evolution of human mathematical ability in classical Darwinian terms. And a fortiori, therefore, the sort of things I've been talking about. It's because it's very. All these arguments are very difficult to frame because they're all, in some sense, just those stories. But
what about our ability to perform very complicated, very beautiful music?
Well, that's not. I think that's. Then again, it seems. You see, I think all these abilities start in some sort of evolved survival situation. I mean, some sort of. To utter different forms of cries, for example, is obviously useful. We know that baboons communicate by different forms of grunting and things of that nature. But I think once you start moving in that direction, the way that this thing absolutely bursts into fruitfulness and suggests that has led one into the encounter with and the subsequent exploration of another realm of reality within which we live our lives. I mean, I think we live in a very multi-dimensional reality. There's physical reality, biological reality, there's noetic reality, mathematics, there's all sorts of things. It's aesthetic. I take the dimensions of beauty. I think that's a real encounter with the way things are. And similarly, I think we have real ethical knowledge. Of course, there again are evolutionary insights into ethical things. I mean, kin altruism and things of that nature, but it doesn't explain radical altruism. So I think we need a much more complex story than the conventional story is able to make intelligible.
I just for a personal note on that, I was once at Aspen Center for Physics and went for a hike up into the mountains, and there was this beautiful mountain and the lake and the glacier, and I sat there wondering, why do I appreciate that? The mountains, the lake, and glacier, they're not good to grow things on, they're evolutionarily useless. In fact, I think medieval people even thought they were ugly because they couldn't grow things. But I mean, for me, it seems like it was just a natural to experience this beauty, and it's hard to see how that would have come from an evolutionary.
That's right. 18th century people were terrified of mountains. They didn't want to go to the Alps.
But but at least a lot of us nowadays, I mean, maybe all don't, but why, we have this
I agree,
it's a similar thing.
It's exactly similar thing, yeah. Yep.
A question on the physics of a resurrected body.
Yeah.
Sure. So Jesus gets a resurrected body, hopefully we will too. Is that matter? Is there a theory that you can apply to try to understand it? And I guess, kind of on a lighter note, for lots of unemployed string theorists, might this be a good occupation? Because after all, there's very little chance of experimental contact.
Well, it's very important, as I'm sure you know, to realize that Jesus was resurrected and not resuscitated, as presumably people like Lazarus were. Lazarus is going to die, but Jesus is raised to some form of new, ending glorified life. That's it. And I see God's creative purposes as intrinsically two-stage. There is the present old creation, which exists at some distance from its creator, from the veiled presence of its creator, partly or perhaps even largely so that creatures may have a degree of independent choice to how to respond, not to be overwhelmed by the infinite unveiled presence of divine reality. A world in which creatures are allowed to make themselves, an evolving world in which death is the necessary cost of the new generations, the life of the next generation, and so on. So that's the world we live in. But I think God's ultimate purpose is to draw creation into a more intimate connection with the divine life. And that is the new creation that's spoken of in the New Testament. And that new creation has already begun to grow, in my view, from the seminal event of Jesus' resurrection. And I think that ultimately all of this creation will participate in the new creation. I think not only human beings have a destiny beyond their deaths, but the universe, which is also going to die, of course, in one way or another, also will have a destiny beyond its death. God cares for the whole of creation, and it matters to it. It's not just there to be the temporary backdrop of the human drama. And our destiny and creation's destiny lie together. And it's extraordinary that's a thought that's expressed in the New Testament. In Romans 8, where it says, creation was subject to futility, waiting the liberty of the children of God, and where Colossians speaks about Jesus as the one who redeems all things, not all people, all things, by the blood of his cross and so on. So there's a hint there. So the new creation is going to be different, and it seems to me that, and Paul was absolutely right, I think, I'm glad to say, in 1 Corinthians 15, to say that flesh and blood will not inherit the kingdom of heaven, nor will the corruptible put on incorruption. There has to be a change. And I believe it is perfectly believable that God can bring into being a new form of matter, so endowed with self-organizing principles that it is no longer subject to the thermodynamic drift towards decay, which is necessary in the matter of this world, because of the reason I've just been talking about. And I think this is where the empty tomb is important. The empty tomb essentially says, it seems to me, that Jesus' risen and glorified body is the transform of his dead body. And the tomb is empty because the matter of his body has been changed into the matter of the world to come. So that in Christ there is a destiny not only for humankind, but for the whole of creation, and indeed for matter itself. I mean, that's a very quick run through. I've written a book called The God of Hope and the End of the World, which has a more extensive discussion of these issues, which they certainly need and deserve. But that's how I think about that. And of course, it seems to me that science of this world cannot speak about the science of the world to come. But it cannot, I don't think it's incoherent to believe that there could be such a form of matter. And science can't deny that.
What do you mean mathematics?
What?
With the same mathematics?
Yes, that's the question.
Does that transcend the barriers?
What do you mean by the same mathematics? I mean, the actual laws of nature will have to be different, obviously.
Will they be expressed in what we would call mathematical form?
Well, I would guess so, because it seems to me that seems to be...
And don't many mathematical theories then, if you start a bunch of things and evolve them under Newton's laws or any other law, they ordered configurations become unordered as you evolve them in time. So how does it go?
Speak of it.
Sorry, if you start with an ordered configuration of points, say, and you evolve them under Newton's laws or Schrödinger equation, you tend to become unordered as time goes on.
That's this world.
Yes, but that's mathematics too. Many different laws will give you
different equations. Well, I mean, there have to be different equations. I mean, if it's different matter, and if mathematics has a role in describing properties of matter, the equations will have to be different. The mathematics have to be different. I don't know what that mathematics is. I'd be very surprised if it comes out of string theory, but that's... but, I mean, it doesn't seem to me to be an incoherent hope. That's all I would want to say.